Okay, hello everyone. I'm Pingfeng Wang from University of Illinois. So on behalf of the organizing committee, I welcome you all to the 7th webinar by the Journal of Mechanical Design. So the central theme of this webinar is integrated design and operation of engineering systems, or we call it IDOIS, with predictive modeling. So I would like to start by thanking Dr. Wei Chen, the editor-in-chief, for dedicating this webinar to the special issue that we recently organized so that we are able to showcase some great work collected in that special issue. And also, I would like to acknowledge the organizing committee. Together with me, Dr. Yongming Liu from Arizona State, and Dr. Sayan Ghosh from GE Global Research, Dr. Piyush Pandita from GE Global Research, and Dr. Faez Ahmed from MIT, and for great effort putting together the webinar. And also thanks to Amy from ASME for the great help throughout the process. So this webinar will feature a special issue recently we put together, and this special issue was motivated by the growing challenge for the increase the system complexity and long design line for the engineering system, so that the post-design activities that greatly affecting the system performance over time. And these activities such as manufacturing, operation and maintenance, and the life cycle, the aspect of the at the post-design stage. So it's getting more and more difficult to precisely model these activities and take into account them in the early design stage. So with the growing capability of predictive modeling, we see that there is a great potential of utilizing advanced predictive modeling techniques to help us address that issue so that we can holistically design the system by considering not only in the early design stage, but also the post-design stage activities. So together with the guest editors, myself, and also several the webinar organizer here, together with Dr. Kotecha Pancher from Purdue and Dr. Dismas Morales from Auckland University, we put together this special issue with soliciting papers in some representative topics such as novel design concepts to consider early design stage and post-design stage activities, and also predictive modeling methods and design methods that to address those modeling and the design activities involving these post-design stage models, and also digital twin and survey and reviews. So throughout this process, we actually collected a really great number of papers, and through this review, we finally have a really nice set of the papers being included in this special issue. So totally we have 13 papers, and coming from these 5 different the themes. That the first is the current literature. We provide a very nice review of what is the current state of the art. And then we have 3 papers in the novel predictive modeling approach, and then the 3 papers in the category of new design concepts, and 3 papers in the novel methodology for digital twin design. And last but not the least, the novel engineering system applications of this IDOIS. So out of these 13 papers today, we are really honored to have 4 of the authors here, and each of them have published at least 1 or more papers in this special issue. And today, they each got around 13 to 15 minutes to share with us about their great work in this special issue. So I would like to remind the audience that we will hold the central Q&A at the end. So we hope that the presentation from the presenters will not be interrupted. And please type your question in the chat box with starting with the question to a particular presenter, please. So without further ado, I would like to introduce Dr. Zhen Hu So Dr. Zhen, who is assistant professor in the Department of Industry and Manufacturing System Engineering at the University of Michigan, Dearborn. So Dr. Hu earned his PhD from mechanical engineering at Missouri University of Science and Technology in 2014, and also his bachelor degree from the Central South University in 2008. Dr. Hu also spent a few years at Vanderbilt University with Professor Mahadevan as a postdoc researcher. Dr. Hu has published over 90 peer-reviewed journal articles and over 40 conference proceedings. His research area include uncertainty quantification, Bayesian data analysis, risk and reliability, structural health monitoring. So his paper was selected in the top 10 best papers in the ASME Design Automation Conference continuously in many years. And he has served as 2022 Technical Discipline Chair for the AIA SciTech at the Non-Deterministic Approach Conference. So Dr. Hu, the floor is yours.
All right, thanks Dr. Wang for introduction. Okay, can you see my screen?
Yes.
Okay, great. Hi, good morning, everyone. So this is Zhen Hu from University of Michigan, Dearborn. So today I will present reliability-based mission planning of off-road autonomous ground vehicles on uncertainty. So on behalf of my collaborators, including Professor Maulik from Oakland University, Dr. Ghosh, Dr. Singh, and Dr. Tao from US Army GVC, and Dr. Yanfu from Ford. So in this presentation, I will cover 3 papers, including 2 papers from the special issue and another paper also published on Journal of Mechanical Design. And we really appreciate the opportunity for publishing. And if you are interested in any of these topics, please look into our details, look into our papers for details. So first, a little bit of background introduction. All these 3 papers we published on Journal of Mechanical Design, we focus on off-road autonomous ground vehicles. So off-road AGVs are vehicles that operate autonomously in the off-road environment. It has both military applications and also non-military applications. For example, for non-military applications include mining, construction, agriculture, and exploration of the Mars. Okay, so for all these off-road autonomous ground vehicles, a very important topic is the mission and path planning, because that governs how the vehicle will operate in the off-road environment, and it plays a very important role in guaranteeing the successful operation of the off-road autonomous ground vehicles. So in terms of path planning algorithms in the past years, there are many approaches have been developed, including global path planning method and the local path planning method. Especially in recent years, for the on-road autonomous vehicles, there are many path planning algorithm or model predictive control method has been developed by using LiDAR or vision-based detection method. But all those LiDAR or vision-based detection method for the on-road autonomous vehicles, sometimes they are not applicable for the off-road autonomous ground vehicles for many reasons. For example, in battlefield, sometimes the enemies can use some techniques to reduce the visibility in the battlefield. And also it's quite sometimes there is a flaw in the battlefield, such that the vision-based detection method using deep learning or computer vision, it doesn't work. Another reason that this method doesn't work is that in the off-road environment, sometimes even if you can see it, but you still don't know if the vehicle can mobilable on that region or not. For example, as shown here, this terrain is pretty flat, but because the deformable terrain, the vehicle may be, sometimes it can pass, sometimes it may get stuck in the deformable terrain. This is a similar situation for the mud pond. So this is also why we need to use modeling, physics-based modeling and simulation to predict the vehicle mobility in the off-road environment to address these problems. And then using the model-based modeling and simulation, we can perform a global path planning to ensure that the off-road AGVs can successfully complete the mission in the off-road environment. So in terms of the model, physics-based modeling and simulation for mobility prediction, we start with some soil map and height map. And we also have a vehicle design in the physical environment. Based on this simulation, we can perform vehicle dynamics analysis to predict the vehicle mobility and also account for the interaction between the vehicle and the terrain to predict the speed of the vehicle and also vertical acceleration of the vehicle. But in off-road environment, a major challenge is that it involves many sources of uncertainty. For example, for soil at any points, there involves many uncertain soil parameters, include the cohesive strength, friction coefficients, buckle density. These are just some examples. And also there's some uncertainty in the slope. As a result of that, there is uncertainty in the vehicle mobility. So as shown on the right, due to the uncertainty in the vehicle mobility, sometimes the vehicle can pass a certain region, sometimes it cannot. So it's very important for us to account for the uncertainty in the vehicle mobility caused by uncertainty in the terrain, soil, and the vehicle parameter. And by considering this uncertainty in the vehicle mobility, we can better design our autonomous vehicle and incorporate the post-design operation condition into the design to ensure the reliability and the safety of autonomous ground vehicles in the off-road environment. So in order to address the uncertainty issue in the off-road environment, there are several challenges that we need to be addressed. First one is the computational effort issue. The high-fidelity simulation model can predict vehicle mobility, right? But it's very computationally expensive. It cannot be directly used in our design optimization or path planning. And so our first paper on dynamics ensemble of Nath model addressed the first challenge about the computational issue. Another second challenge is how to incorporate the reliability constraint into the real-time mission planning. The other of our journal mechanical design papers address the second problem. Here, I will give a brief overview of what we have done in these three papers. So for the first paper, is the overview of this topic that we cover here is that we first use the physics-based simulation model. By giving some paths, we generate some synthetic mobility data. And based on synthetic mobility data, then we can use the AI or machine learning model to build a data-driven and dynamic mobility prediction model. And then this data-driven and dynamic mobility prediction model is very cheap to evaluate, but they can accurately predict the vehicle mobility, and then it can enable us to perform model-based mission planning. However, in our research, we found that not all current available methods include STM, NUXNet, GPNUX. They have an issue that they cannot accurately capture nonlinear dynamic behavior of the vehicle vertical acceleration due to the nonlinear dynamic system. For example, here there's the large errors in the peaks of the acceleration. So based on this observation, we also noticed that the vehicle on certain paths, the vehicle dynamic exhibits different dynamic behaviors in different regions. So for some region, it has some low frequency dynamic behavior. For some region, it has a high frequency vibration behavior. So based on this observation, the idea that we proposed here is that we partition the dynamic region into different segments. So different segments capture different dynamic behavior of the vehicle. And then we construct individual Nath models for different segments. And after that, we ensemble them together By doing this, it can improve the prediction accuracy of the data-driven mobility model. So this is the overview of the flowchart. It involves several steps, including synthetic data collection, partition of the dynamic domain, and training of individual models, and then finally ensemble them together by considering the prediction uncertainty. So here are some results. This part of results shows that STM, NUXNet, GPNUX, without using any ensemble, you can see that there is some errors in the, at the peak of the vertical acceleration. But after applying our proposed method, we call the DINA, is dynamic ensemble model. We also propose another method called DINA diff. You can see that the accuracy has been increased significantly, especially if you look at the error comparison here. Before applying the dynamic ensemble method, the error is at the level 7.5. After we apply the ensemble, the error has been reduced to around 2.5. So after we have the data-driven mobility model, the next question is how can we use that for mission planning by considering reliability? And then this has been addressed in these two JMD general mechanical design papers. The overview of the optimization problem as shown here. So our objective function is to minimize the travel distance or travel time of off-road autonomous ground vehicles. At the same time, we consider the uncertainty in the travel time or length caused by the uncertainty in the soil properties. So we formulate the overall problem as a robust reliability-based design optimization problem. The objective function is a robust design objective function. And at the same time, we add a reliability constraint into the optimization problem. Here, the reliability constraint we added here is called the mission mobility reliability constraint. With this mission mobility reliability is also proposed to be in one of our general mechanical design paper. So in order to solve this optimization model, what we did is that we created a reliable and robust randomly exploring random tree algorithm. Basically, we modified the RT star algorithm by incorporating reliability and reliability constraints and also the robustness consideration. So every time you add a random tree in the search domain, we verify the reliability constraint to see if it can be satisfied. So by doing this, the final identified path from RT star and can not only be the shortest, but also can satisfy the reliability requirement. But the issue for this problem is that evaluating reliability is very computationally expensive, even if we use the data-driven mobility model. So if we use the direct Monte Carlo simulation model, the RT start for the path planning may take maybe 1 or 2 hours. It's not practical, not computationally feasible for practical application. So to address that issue, in this journal mechanical design paper, we propose an autocorrelation rate based method. Basically, we compute the autocorrelation rate at every spatial location. By doing that, we can convert the probabilistic mission planning problem into a deterministic mission planning problem by reducing the computational complexity. So the proposed method starts with the soil map, slope map and physics-based simulation by considering uncertainty, and then we generate a probabilistic map. Using a probabilistic map, we can generate a group of autocorrelation rate maps. And then we integrate the autocorrelation rate maps into the RT star, and then we can identify the paths that satisfy the reliability requirements. So here shows some results that we got from our proposed method. If you look at this figure in terms of the computational time, our proposed method is RT star OC. You can see that the computational time of the RT star OC is almost exactly the same as the original RT star, meaning that the computational complexity has been reduced to for the probabilistic planning to the deterministic one. And also, if you look at the comparison of the identified paths here, the identified path from RT-OC is exactly the same as the R2 RT star, and meaning that we reduced the computational time, but we didn't sacrifice the accuracy. And also the reliability requirement has been satisfied. So we also go one step further by looking at multiple vehicle path planning. We have developed a buyer-inspired approach. Basically, we model the map as a graph, and then model the links of the graph using this equation. And then finally, we solve this optimization problem using Safari solver. So by using the Safari solver, we also start from the simulation. We first generate go and the no-go map by considering reliability, and then we generate a matched map. After that, we're using the proposed methods. We can efficiently identify the paths, satisfy reliability requirements. Most importantly is that if there is an obstacle in the middle of the path, the algorithm can very quickly perform replanning. So we also applied it to this path planning for multiple vehicles. Suppose that we have 3 vehicles, S1, S2, S3. We want to reach it to 3 targets. The proposed method can automatically allocate these 3 vehicles to the 3 targets, and at the same time, identify the shortest paths and satisfy the reliability requirements. And the computation time you can see here is also much lower than the traditional Dijkstra-based method. Okay, so in conclusion, here I give an overview about our 3 papers published on Journal of Mechanical Design. In the 3 papers, we have developed a dynamic ensemble method for mobility prediction. We also proposed a reliability-based machine planning algorithm by reducing the computational complexity and for multiple vehicle mission planning. And this part of research is supported by Automotive Research Center. We would like to thank the ARC for the support. Thank you.
All right, I will go ahead and introduce the second speaker. Dr. Zhimin, she is an associate professor in the industrial engineering from Rutgers University. Got a PhD from University of Maryland in the reliability engineering program. He has done really on the design for reliability in many different areas, and also have won different external and internal award, including the Rutgers Internal Assistant Professorship Award. And today he talked about a nice approach about a hybrid model and the data-driven approach for the predictive controller design. Without further ado, please go ahead, Dr. Xi.
Okay, first, thank you for the introduction, Yongming. Are you able to see my screen?
Yes, go ahead.
Good. So my topic is about autonomous vehicle trajectory tracking. And particularly, we see there's a potential issue if you ignore the model and environment uncertainty in this process. And our work is based on so-called model predictive control. And we use so-called bias learning, try to further improve this model so that we can perform more reliable trajectory tracking. And I would like to thank my PhD student, Li Chuan Zhen, for her wonderful work on this project, on this work. So here's the outline. I will give an introduction, then I'll move to the proposed bias learning-based MPC. Then I will show you 2 results. One result is from the color simulators, another is from the actual real-world experiment data. Then I'll draw some conclusion. So first of all, we realize there are some potential reliability issue for path tracking if you ignore environment and model uncertainty. At the left-hand side, I show you a good situations. We have good weather condition, good tide conditions. On the right-hand side, we have relative bad situations. Now, if you rely on model free, let's say PID versus PID control or other low fidelity model, you will have a reliability issue. You can see from the right-hand side. So we try to address this problem in the future for the future autonomous driving situations, and then we need to formulate this problem. Now, in terms of problem formulation for the path tracking, here is a simple setup. We consider vehicle state as represented by this S available. It has 3 states, E1, E2, and in the diagram, E1 basically is a cross tracking error. compared to the vehicle actual position versus the ideal path. Then we have E2 is basically the vehicle current heading direction angle compared to the angle from the ideal path. And we have its error rate. So we have 4 variables for the to define the vehicle state. And the vehicle action space is only 2 dimensions. One is the steering angle delta, another is a vehicle translational velocity. Now, since we're going to rely on this MPC model predictive control, we have to use a physics-based model, vehicle dynamic model. And the model we're going to use is so-called the bicycle model. So basically, in this simplified version of the vehicle dynamic model, we merge 2 front tires to become 1 front tire, and merge the 2 rear tires become 1 rear tire. So it seems like a bicycle. So that's why it's called a bicycle model. And in this bicycle model, we consider also the slip angle of the front tire and the rear tire. And you can see in this diagram, the front tire has a heading, the steering angle delta, but the actual motion of the front vehicle is different with the steering angle. So we have the alpha F as a slip angle from the front tire, and also we have the slip angle alpha R from the rear tire. Okay. Now to quantify this vehicle dynamics, we have differential equations, and so we have all the vehicle states can be represented by this so-called baseline vehicle dynamic model. Now, the proposed approach is that because of these simplifications, if we consider the actual motion of the actual vehicle, this simplified model will give us some error, and that error could lead to unreliable path tracking problem. So the proposed approach is that we're going to use this baseline vehicle dynamic model, but in addition to that, we're also going to add a machine learning model, and this machine learning model we propose is so-called we try to learn the bias of this baseline model compared to the actual observation. So that's the bias learning model. We propose 3 different methods to do that. And the first is a Gaussian process. And we also use a recurrent neural network, an offline version and an online learning version. So 3 models to try to learn the bias, and we did some comparison. So in this setup, the input we're going to take is, of course, 4 vehicle state and a 2 vehicle action space. And we also have the environmental variable, which captures the tire and the ground friction coefficient for the vehicle. And the output of this model is basically the predict the next the states of the vehicle at the next time step. So in terms of the overall control principle, based on this BL MPC, at every time control cycle, which is typically 0.1 second, we need to solve an optimization problem. So we try to minimize, of course, minimize this objective function. And in this objective function, it contains 3 terms. The first term is basically S indicating the tracking error. And the second term basically means we try to minimize the change of the steering angle as much as possible to make a stable control. And the third term, basically, we try to make the vehicle run as fast as possible to the speed limit. But of course, we need to make this stable. Now, in order to learn this bias model, we have to get the training data to learn this bias model. And as I previously explained, we have input space defined from 4 vehicle, the vehicle state with 4 variables, and a vehicle action space with 2 variables, and 1 variable for the environmental uncertainty. And then the output we're going to take is the actual observed vehicle state, subtract the predicted vehicle state from the baseline bicycle vehicle dynamic model. Now, when we did this training in the simulator, we conducted about 30 minutes training, and the 30 minutes means, and every control cycle is about 0.1 second. So 30 minutes means 30 times 60 times 10. So we'll have about 18,000 training data point for 30 minutes simulation. Now, in order to build this bias learning model for 13,000 data point, the traditional Gaussian process has an issue because of this large data size. So that's why we adopted this so-called scalable variational Gaussian process. We basically minimize get the representative sample point, so we can reduce the the matrix inversion operation, so that this Gaussian process can be used for the bias learning. Now, the second model we used is a recurrent neural network model, and I'm not going to show the detail about this model, but the recurrent is basically the hidden node in the recurrent neural network model is the key thing. And each hidden node is represented by a so-called active function. And that active function will take all the 7 variables for the inputs, xt, and also will take the previous hidden state. So that's why it's called a recurrent neural network, and also has a bias term. And we can define different number of hidden nodes and a different number of layers, and the output will be predict the next time step vehicle states. So that is the offline version. And also, in addition to that, we also have an online learning version. So the online learning version is basically, we have an offline RNN model learn, but when the vehicle is really doing the control, it also observes the actual, the bias, and it tries to further update what is those weight coefficient in the offline learned RNN model, so that we expect this model, online learning model, will be more accurate. Now, to validate our proposed work, we find a real world, the data set for autonomous driving. And this is a new scenes data set. It has all different situations. And for this particular problem, because we are working on a lower level control problem, we need a lot of detailed information. And this new sense CAN bus expansion data set able to provide the information we need for our the validation work. So here I just show you one of the scenarios. For example, it provides a high precision map, and it has its idea defined path. Then it knows the vehicle actual position, and it knows the vehicle actual pose all the time. And at the same time, at any time instance, we know all the vehicles real vehicle speed and wheel speed. So we know all the information we need for our model to do the validation. So that's why we use this new themes CAN bus data set. Now in this data set, we total have 1,000 different driving situations. And we split those data set into a training data set, about 70%, then 20% used for validation, and 10% for testing. Now, to quantify the tracking error, accuracy, and we get the mean absolute error as a metric. And once we use try to validate for the test data, we calculate all the the MAE, and that we got the average value. Now we compare the 3 methods. One is a simply baseline model, use a baseline model based on the for the MPC. Then we have offline RNN and online RNN. And you can see the MAE difference. Basically, the online RNN model provides us the best tracking error because the minimum tracking error from the density functions. And the baseline model provides us a relatively large tracking error. Now, that is a result from the the existing experimental data, but we also further confirm those results using our color simulator. So in the color simulator, we have different driving maps, and we have different driving situations, and we have we of course use some training as the training scenario. Then we do the test at the actual situations. Then in this table, I show you 3 columns of results. Basically, mu equal to 1 until reduced to 0.25 means become worse and worse environmental conditions. So we have hard and hard control situations. Then we compare the baseline model and with the Gaussian process and the offline version RNN and online version of INM in terms of tracking error. So in all these scenarios, the online version INM provide us a minimal tracking error. And here I show you one of the comparison between MPC and the BIMPC using the color simulator. So this is a situation we have good weather conditions, and the bottom figure shows you the actual tracking, cross-tracking error with respect to time. Then we have better situations. So compared to MPC and BMPC, BMPC always provide kind of a smaller tracking error if we are able to learn those bias accurately. So the conclusion is that we basically proposed bias learning based MPC, and that can generate more reliable control under different driving situations for autonomous vehicles. And we also use the IMM, and this IMM with online learning feature since performs best. And because the reason is this model bias model is also adaptive to the real-time situations. And in our problem, we studied the IMM performs better than the Gaussian process, and especially because it has its recurrent feature, which is important in this setting, because all the previous state will determine also somehow the next future state. And that can be captured by the IMM structure. So that's all for my talk.
Okay, thank you. So our next speaker is Dr. Paromita Nath. Dr. Nath is assistant professor in mechanical engineering department at Rowan University. She received her PhD in civil engineering at Vanderbilt University. Dr. Nath's research interests include uncertainty quantification, Bayesian inference, process design and control under uncertainty, and machine learning with application in additive manufacturing, healthcare, and power systems. Her current research focuses on building and implementing a probabilistic digital twin for additive manufacturing, and also on studying the process structure property relationship in additive manufacturing. So Dr. Nath, it's for you.
Thank you, Dr. Ghosh, for the kind introduction. So I will be talking about probabilistic digital twin for additive manufacturing. Okay, so additive manufacturing is a technique that is widely popular in this world nowadays, but due to the variability in the product quality, it is still not widely adopted across all industries. The trial and error process of finding out the optimal process parameters is expensive, and no physics-based model is accurate. So there is a push for using an integrated process of integrating physics-based model predictions with some experimental data. So there is this need for optimization of the AM processes and also for process optimization during the manufacturing, which is basically process control. Now, when we talk about models and about additive manufacturing in general, there are different kinds of uncertainties and variabilities in the AM processes. These uncertainties, which are inherent to the system and the process, are the aleatory uncertainties. And then there is lack of knowledge, which leads to epistemic uncertainty that could come from model parameter, model form, and also from input uncertainty. Additive manufacturing is a complicated process, so all these processes need to be defined by different physical processes. So you need multi-physics, multi-scale models to define the AM processes, which leads to more sources of uncertainty. So we need to quantify and reduce the uncertainty, and that can be done under the Bayesian framework using verification, calibration, validation, using better characterization through experiments, etc. And then we also need to do uncertainty management. So we have reduced the uncertainty that we can, but then we still have to live with some of the uncertainty. And that is where you need process optimization and control under uncertainty, which is then process optimization that requires offline information, and then process control, which gets the most up-to-date knowledge during the manufacturing of the process. So this leads to the concept of digital twin, but since there is so much uncertainty in the process, this is not a deterministic digital twin, but a probabilistic digital twin. Now, how do we define a digital twin? The work on digital twin is a few decades old, and one of the definitions that Greaves and Vickers came up in 2011 is that digital twin is a single instance of a physical system, and the data collected from this single instance is used to update the virtual representation. And over time, this digital twin now represents that single instance with increasing fidelity. So there are three different elements of a digital twin: the physical system, in our case, it is the printer itself, and a virtual representation of the system. And now these two systems are connected through two interconnections. So there is a connection from the physical reality to the virtual space and from the virtual to the physical connection. So one leads to the communication of sensor data, which is for data fusion, diagnosis, and model updating, whereas the other connection here leads to the decision making, and how do we update using the updated prognosis model, how can we make decisions for the physical reality. So in this work, we are concentrating on digital twin for the laser powder bed fusion process. So the physical process is actually the additive manufacturing machine itself. The machine the digital model, which consists of the CAD model and the STL file, feeds into the AM machine. And during the manufacturing, we can monitor the system using the monitoring system. The virtual representation of this would be a physics-based model. And these, as I said earlier, one model may not be enough, so we may need a suite of physics-based models. Now, this is extremely expensive, and for decision-making while the process is going on, we need faster models, and that is when we substitute this with surrogate model, which gives us the prediction or the predicted QOI. Now, these two are then connected using the sensor data, which goes from the physical reality to the virtual representation. We do the model updating, find out what should be the print parameters for the future layers, and we feed it back to the physical reality. And this goes on for all the layers of the laser powder bed fusion process. So the basic method for this work is based on the concept of digital twin for a laser powder bed fusion, where our quantity of interest is the lack of fusion porosity due to insufficient melting. Now, when we have LPBF process, there are scans that are going on like this, and based on how much is the distance between the two, called the hatch spacing, and what is the thickness of each layer of powder, we will have some sort of unmelted volume fraction here, which is basically the powder that gets trapped between molten volume and has never been melted because of insufficient heat in the process. So if we want to control this unmelted volume fraction, which is basically a measure of porosity, we need to construct and deploy a digital twin. And this consists of 9 steps. So we start with an initial virtual representation. We validate that virtual representation. We collect monitoring data, diagnose and infer the quantity of interest, which tells us what is the current state. Then we update the model. We find out what is the initial process optimization, what is the initial process parameters that we should start the manufacturing with. Then we can do the prognosis of the quantity of interest in the future step. Then we can optimize, which is the process control during each step of the printing or for each layer. And then we also need to validate our digital twin. So the initial virtual representation here, we are using a very simple Rosenthal model, but whenever high fidelity models are available, you can obviously use that. So this geometry-based model first starts with finding out what is the width of the melt pool, and from the width we can calculate what would be the unmelted volume fraction. Now this initial representation can be validated, but we are not collecting data to validate this model at this step. We will use previous experiments or experimental data from literature or publicly available data to validate this. For this, we could use different kinds of validation matrix, but in this paper, we are using the model reliability matrix, which is a distance-based matrix, which tells you what is the probability that the difference between the probability of the difference between the prediction and the observation. If it is within a tolerance, then we are okay with this model, and then we can proceed with that. If not, then we need a better model. So next, we are going to do the diagnosis and inference of the quantity of interest. And for a digital twin, an effective monitoring system is an online, non-destructive, non-contact monitoring system, which then gives us the current state of the manufacturing process and also the part. And we can then find out our quantity of interest. If the quantity of interest is directly observable, for example, surface roughness, which we can measure using a profilometer, or temperature distribution, which we can measure using a thermal data or thermal camera, then it's simple. But some of the quantities like residual stress or other subsurface defects and porosity cannot be directly observed. And so in that case, which is the case in this paper, we need an indirect measurement technique. And so here, if our quantity of interest is porosity, we do an intermediate quantity measurement, which is through the IR camera, we collect the temperature data, and then we infer our porosity from this melt pool dimension that we get from the collected temperature data. And finally, when the part is actually finished, we can use offline techniques like X-ray computer tomography to find out what is actual porosity of the part. Now, because of this indirect measurement, we need a two-step surrogate model. The first step now predicts the melt pool width, and the second step predicts the unmelted volume fraction. The model parameters and the discrepancy term are calibrated using the temperature data, because that is the only data that we are able to get during the manufacturing process. And this model, which is up with the updated parameters, is now used for decision making, which is the online process control part. So the initial process optimization, or finding the optimal parameters before the printing has started, is based on data that is available before manufacturing. So it does not consider the most up-to-date knowledge of the manufacturing process. And here, to consider the uncertainty, we are using a robust design optimization algorithm, where we are not only interested in minimizing the mean, we are also interested in minimizing the standard deviation of the objective function, thereby minimizing the variability in the process. So once we do that, the manufacturing starts with the optimal process parameter. We use the monitoring data to infer what would be the quantity of interest or the porosity when the part is finished. We can then model the discrepancy term, and we can calibrate it using the monitoring data. This is our updated model, and this updated model is used for decision making. How do we make the decision during process control? If the predicted quality of the finished part is better or equal to the target quality, then we can just continue as is. If it is less than the quality or less than the target quality, it is like very, very bad, then there is no point that we cannot salvage this part at all. Then we can terminate this manufacturing process. However, if it is somewhere between the target quality and we can maybe change some process parameters and do something about it, then we would do the modified process parameters. We'll change the process parameters and try to salvage the part. Which then finally brings me to the validation of the digital twin. Now, digital twin is specific to the printer, the printing environment, and the part being printed. So when we need to validate the digital twin, the experimental data has to come from the same system. Here we do the two-step validation of the digital twin because our quantity of interest is not observable during manufacturing. So we do the intermediate or partial validation using the melt pool width, by using the data that we collected online, and the final validation is when we collect data offline after the part has been printed. And here again, we use the same model reliability matrix to do the validation. So this is the summary. We start with a virtual representation, do the two-step surrogate, validate the initial prediction model. We collect data from the online process monitoring system, find the optimal process parameters, collect experimental data, calibrate the model parameters, and that is how we update the model, do the partial validation, estimate the quantity of interest. If it is okay, then we continue. If it is too bad, we terminate the process. And if it is somewhere in between, then we do the new process parameters and continue the process like that. So now I very quickly will show you how do we do this, how do we implement that. So we can consider a very small part, and we are trying to control the unmelted volume fraction here. The uncertainty in the material parameters is the aleatory uncertainty, and the epistemic uncertainty is captured through the model discrepancy term. We use our initial virtual representation using the Rosenthal equation I showed before. We have the two-step Gaussian process surrogate model. We validate that model using the data that is already there. And then we do the offline process parameter where we find the initial design parameters, and then we can start the printing. Here we simulate a malfunction in the print environment, and we say that whatever is the laser power applied, it is realized like 10 watt less than what was specified. And so then we collect data using infrared camera, and we can finally say that we will get offline data from X-ray tomography. So we can also do the discrepancy term and model updating, and we can see that as we collect more and more data, the uncertainty in the discrepancy term reduces. So the posterior 1 is here, and when we see posterior 5, the red line here, it is much less uncertainty. And this updated model is used for decision making. So if we see how does this work, if we do the process control, we see that our parts quality is very close to the target that we had. If we do not do any process control, then the quality of the part deteriorates, and it's very far away from what we had actually intended it to be. So finally, in this work, we propose a probabilistic digital twin for optimization and control in the LPBF process. And we see that the parts with control exhibit better quality than the no control case. The future work is to use better models, more sophisticated models, which might require multi-fidelity modeling approach. We need to investigate the effects of dwell time. How can this model be scaled, or how can this methodology be scaled for larger systems? And we also need to experimentally validate the proposed method, because right now we have just used synthetic data generated from the models. With this, I'll conclude the talk, and thank you.
Thank you, Dr. Nath.
Thank you. Our next speaker is Maulik Kotecha. Maulik is a PhD student in the J. Mike Walker Department of Mechanical Engineering at Texas A&M University, working in the Product Synthesis Engineering Lab with Dr. Dan McAdams. He's done a lot of research on nonlinear dynamics, computational mechanics, and focused on engineering design. In this paper, they're going to be presenting an approach for functional modeling based representation of digital twinning architectures. The proposed architecture representation approach, it'll open up new avenues of research and can help improve the design process for product digital twin. So let's let Maulik share his research, and I believe there's going to be a lot of questions as well. So the topic is super interesting. All right, Maulik, floor is yours.
Yeah, thank you for the warm introduction, Dr. Pandita. Let me share my screen. So today I will be talking about a functional modeling based digital twin architecture representation, and I will explain that using an example of a COVID-19 breathalyzer kiosk. Apart from me, the authors of this paper are Dr. David Stack and Dr. Dan McAdams. Both of them are professors at Texas A&M University. So let me begin with some definitions of digital twin. So digital twin is a virtualization or digital representation of a physical object or system. It may include virtualization of its structural components and environmental conditions depending on the chosen fidelity of the representation. The key feature of the digital twin is the real-time bidirectional exchange of data and information between physical product and its virtual counterpart. And digital twins are designed for various twinning purposes, such as asset tracking or remote monitoring or machine health monitoring or fault prognosis. And depending on the intended use, the synchronization frequency and the fidelity of the model changes. So, and also the digital twins are designed at various scales. So there are examples of digital twins of big cities, some examples of factories and plants. There are digital twins of cars and airplanes, and there are digital twins of processes as well, digital twins of components as well as the whole products. So for the purpose of this study, to begin with, we will focus our study on digital twins of products. So for the design of digital twins, there are numerous frameworks and reference architectures available in literature. A couple of them are displayed on the slide for reference. So although these reference architectures provide an outline and some sort of guideline to the designers in their design, to guide the designers in their design process, they do not offer sufficient room to answer questions like how does change in product architecture of physical product will reflect in the architecture of digital twin. So with the motivation of answering research questions like how does product architecture of physical twin affect the architectures of digital twins, and how does twinning purpose affect the digital twin product architecture, and with a motivation to equip the digital twin designers with a familiar approach for early stage design concept generation and design synthesis, we proceeded with functional modeling based architecture representation. So just to note that it is just one of the familiar ways to the designers, and it is just one such approach. So although the audience of this webinar might be quite familiar with the concept of functional modeling, it's customary to give some background. So functional modeling is basically an abstraction technique that involves decomposing product or system's overall function into smaller and solvable functions. So first we generate a black box model which represents the overall function. Then we create function chains based on sequence of occurrence of these functions. And then we aggregate these function chains to create our functional model. So it is basically a familiar approach to the design community, and it enables designers to make critical design decisions at the conceptual design stages. And function basis is basically a clear and consistent lexicon of functions and flows in terms of verb object format, and it comprehensively describes the mechanical design space, and it provides us with different abstraction level. So based on our design purpose, we can choose different abstraction levels for our functions. And functional basis enable design automation through organized storage and function information retrieval. So with this background on functional modeling and digital twinning, we created a black box model for a physical twin digital twin pair. So here is in this black box model, we have distinguished signals of data, information, and status, since they are profusely used in digital twin representations in the literature. So data is basically the data collected from the sensors, be it on the physical product or some environment data collection. Then information is something based on which we make decisions. So it's sort of a process data, and status is the representation of the status of the components in the physical twin. So let us begin with begin to explain our approach using an example of a breathalyzer designed to screen COVID-19 using the breath of the subject. So this breathalyzer we designed as a rapid response to COVID-19 pandemic. And this is a moderately complex product with 13 sub-assemblies and around 170 unique components. And it involves interdisciplinary knowledge and efforts. And the twinning purpose for this product was to remotely operate the breathalyzer and fault prognosis of the components. So following the standard procedure I described earlier, we created a functional model for the physical twin of the breathalyzer first. And I'm showing the mappings of a few structural components to their respective functions here. We then followed the same procedure to extend our functional model to the digital counterpart. And in this particular model, we used standard flows to represent standard flows observed in functional basis to represent the digital twin as well. However, in this model, we cannot distinguish between data, information, different types of model, different types of rules that we use to evaluate our decisions, and the readily available knowledge bases that we use. So in our revised approach, we extended the functional basis to additional rules. So we added additional flows. So we added flows such as data, information, then status, then knowledge, models and rules, as observed here, and so that it could help us distinguish during the concept and function synthesis stage. And our ongoing work is to rigorously test the applicability of these newly introduced functional flows and analyze these functional models of digital twins as network or graphs. And we are also working on to developing a multi-layer graph representation approach for these models. And also our next future work is to find appropriate measures to evaluate similarities and dissimilarities between two or more digital twins. Next, we'll proceed to identify modules in digital twins based on the similarities and dissimilarities. And finally, another ongoing work is on the design heuristics development for the design of digital twins. With that, I will end my talk, and I will thank our sponsors and other contributors who helped in developing the COVID-19 breathalyzer. If you have any questions, suggestions, or collaboration, please contact either me or Dr. McAdams. Thank you.
Thank you, Maulik.
Yeah.
Great. Thanks to all the speakers. So with that, maybe we can start with the Q&A session. What we'll do is I will go through